Hi there. In this lecture, we're going to see a little bit about sensors which have emerged in the last decade or so, and wireless networks that might be joining them. What do I mean by a sensor? This is an example of a sensor I have here, which was originally fabricated by researchers at Berkeley, then later on made by a company called Crossbow, which has later on been acquired by another company, Moog. I'll tell you a little bit more about these kinds of sensors, why they have emerged, and so on and so forth. But let's start at a much more broader or higher level. So everything is getting smaller all around us. In fact, the smallest state-of-the-art transistor that's being made today can be made from a single gold atom. Of course, this is still in research, not yet in industry. But just imagine a world where you could make a transistor of just one gold atom. And let's do some calculations just for fun. Pentium P4, which is a fairly old processor by Intel, contains about 42 million processors. The atomic weight of gold is about 196 to 200, depending on which isotope you look at. 1 gram of gold contains 3 times 10 to the 21 atoms, which means that if you use all the atoms correctly to make one transistor each, then you can make 7.5 times 10 to the 18 Pentium 4 processors from 1 gram of gold, which means that from 1 gram of gold, you have enough processors, Pentium 4 processors, to give each person in the world a billion Pentium 4 processors. That's with just 1 gram of gold. Okay, so you can imagine that as these, what are known as form factors get smaller and smaller, as the sizes get smaller, you can make many more of these sensor nodes, many more of these processors. In general, the speed up of a CPU is directly proportional to the square root of the transistors that you can put on the die. So we are not talking very far from reality with these ballpark calculations. But of course, we are pretty far from this reality because, after all, you still cannot make in a production a transistor from one gold atom. But essentially, the point I'm trying to make here is that everything is getting smaller, and it's easier and easier to make smaller computers such as this one over here. So sensors have been around for a long time. Coal mines have used, and all kinds of mines have used sensors for carbon monoxide and carbon dioxide. In the old days, when we did not have technology, these sensors used to be birds in cages. This is where canary in a coal mine, the phrase comes from. Essentially, if the bird died, you knew that something was wrong, that the level of carbon monoxide in the mine might be too high, and it was time for the miners to get out. Today, of course, many mines in the world, not all, but many mines use advanced technological sensors. Industry has used sensors for a long time. For instance, on the assembly line where cars are being manufactured one step at a time, you need to use sensors so that the assembly line is moving all the time. Today, however, we deal with excessive information, and we need to process this information data and convert it into knowledge. For instance, environmentalists might want to collect data on an island which is uninhabited, where there are no people and where the terrain may be inhospitable. Armies might want to collect data in the battlefield without putting the lives of the soldiers at risk. And in general, humans want to collect data from across a wider geographical area, for instance, around a volcano, where they might want to measure earthquake movement, volcanic movement, and predict the movement of the volcanoes based on the sensors. You really don't want to have people over there mucking around when a volcano might erupt any point of time. And this is where sensor networking technology comes into place, where you might deploy, say, a few hundred of these around the volcano and then detect acoustic movements which might hint at the volcano erupting in the near future. So the growth of any technology, such as sensor networking technology, but in reality any technology requires three components in there. It needs hardware, good hardware. It needs good operating systems and distributed protocols, especially when you have the hundreds of these sensors networked with each other. And of course, you need applications. We won't talk much about the applications. Let me just say that there are both military applications for these sensor networks as well as civilian applications such as the environmental observation as well as the case of monitoring volcanoes. So these sensor networks have been deployed in cases where you want to monitor the movement of whales in the ocean, where each whale has been fitted out with a sensor, where you want to monitor the temperature and humidity in a forest in in an island, and for instance, the Great Duck Island, which is one of the islands that has a very interesting ecosystem, was outfitted with sensors to measure the temperature and humidity inside the forest. And then, of course, the volcanoes in South America have been outfitted with sensor networks to measure their activity. So let's discuss the other two. The sensor nodes themselves have emerged because of several trends. First of all, there is Moore's law, which says that, in general, Moore's law has said that the processing capacity doubles every 18 months. Nowadays, this processing capacity stands more for the number of processors you can put per die and less for the CPU speed. But in general, over the last few decades, Moore's law has made processors faster and faster. Wireless communication is also advanced. And then finally, you have MEMS, which is known as micro electromechanical sensors, where essentially you have sensors that convert some form of energy into an electrical impulse, which can then be sent to a processor so that the processor can then process it. And that's essentially what's going on with these sensor boards over here. So you have this board which has the processor over here. You can see it's a 900 megahertz processor here. And then it has a little bit of memory on it. I'll say a little bit about how much memory it has in a little bit. But what you do is you attach this sensor board, which has a bunch of sensors on it. So this has an acoustic sensor, a sound box, a thermometer, and a few other sensors. And you attach it on top of this, essentially. Let me make sure I'm getting this the right way here. And voila, you have a working sensor. Sensor board where the sensors on this top board can convert some form of energy. For instance, the microphone on this would be able to convert sound energy into an electrical impulse, which is then sent over to the processor, which is also on the board over here, which can then process it according to the application that you've written. Second, it needs a microprocessor, as you've seen here. Third, it needs a communication link, and in this case, you have this wireless antenna. So this is the wireless communication link, so that this sensor mode can then talk with other sensor modes out there, and they can network together in a wireless network. And finally, you need a power source, because these are likely to be deployed in terrains where it may not be possible for humans to go out there and recharge them, and of course, it may not be possible to power them using just regular AC electricity off the wall. You need batteries, and this particular model has 2 AA batteries running on it. So the sizes of these modes are very small. This mode that I've shown you is called a Mica mode or a Mica mode. And then there are smaller models. A Mica dot mode, which is also manufactured by the same company, is smaller. It's also running the same CPU, 900 megahertz, and it has, as you can notice, a wireless antenna. Intel modes were manufactured by Intel subsequently. Here's an example of an Intel mode for you. And the Intel mode, of course, typically has an ARM processor. Here I have the Intel mode has two pieces. The sensor board is on top. This is the sensor board over here. And then the other board is on the bottom. And you can see it says Intel Research over here. And of course, it has batteries. In this case, they are lithium batteries running over here. Okay, and there is an on button here. You switch it on, and after a while, well, you can see that it starts blinking over here, which means that, well, now it's active. It went from white to blue, and it means that it's now active. Let me switch this off. And then there are other sensor modes like this, which have been created that are even smaller. For instance, Golem Dust, which is one of the sensor modes that was created by Crossbow, had a volume of only a few cubic millimeter, which is really, really small. It's much smaller than a typical penny coin that you might find. In any case, in all of these sensors, everything is on one chip. So you notice that when you have this processing board and this sensor board, everything is on just one chip. There is no other peripherals you can attach to this. There is no disk over here. There is no monitor over here. There is no mouse. There is no keyboard to this. Everything is on one chip. So this consists of the processor, the transceiver, which is a fancy word to say transmitter plus receiver. Essentially, this is the wireless antenna, the battery, the sensors. And it also contains a little bit of memory and, of course, buses to connect the memory with the processors. These are very wimpy machines. The Mica mode, for instance, has a 4 megahertz processor. It's got a wireless bandwidth of about 40 kilobits per second. it's got only 4 kilobits of RAM. So that's the amount of RAM you have, not 4 megabytes, not 4 gigabytes, which you might find on your workstations today, but just 4 kilobytes. This is really, really puny. This is very tiny. It has 512 kilobytes of serial flash, but essentially you need to fit almost everything in the program on 4 kilobytes of RAM. If you let it run on full blast on the batteries, then it lasts for only 7 days, which means that it's very important for programs that you write to conserve the energy, to conserve the battery. You don't want to be running at full blast all the time. You want to potentially go to sleep at some point of time so that the sensor node can then save its energy for later on. So there are many different kinds of sensors that are available. You could have acceleration sensors, vibration sensors, which might be useful on the battlefield to detect tanks, sound sensors, gyroscope sensors, tilt, magnetic, motion, pressure, temperature, of course, light, moisture, humidity, barometric. A variety of sensors can be outfitted, and in fact these sensor boards can be daisy chained on top of each other. So you can take one more sensor board and put it on top of this, and then you can stack them on as you desire. Other deployments, for instance, in some of the metros in some of the larger cities in the world have used chemical sensors such as carbon monoxide, carbon dioxide, and radon sensors, as well as biological sensors which detect pathogens. In some cases, actuators are used too. These involve mirrors, motors, smart surfaces, and micro robots. So when you have sensors on the same board as a processor, how do you connect them? Well, typically on these boards such as the Mica Mote, the bus has to be a low power and fast bus, and the bus used on these is called the I2C bus, or the Inter-IC Connect bus. This was developed by Philips. This connects the sensors to the microprocessors. It's very simple. It has only 2 wires. Both the wires are bidirectional. One of them is for data. It's called the serial data bus. The other one is for the clock, which is called the serial clock bus. The serial clock bus is typically used to make sure that the sensors and the processors are talking at the same speed so that they can send data to each other over the serial data bus. Even though this has only 2 wires, it has a fairly high bandwidth, 3.4 megabits per second, which is high enough for a computer as puny as this. What about the transmission medium? Well, in all of these cases, whether it's a Mica Mote, whether it's the Mica Dot Mote, or whether it's the Intel Mote, the communication medium is radio frequency, which is a typical communication medium that, for instance, your cell phone or your laptop uses when it talks to a base station. Essentially, you're sending RF waves out over the wireless medium. This is a broadcast medium, which means that when one sensor is talking to another, the second sensor needs to receive the packet from the first sensor, store it, process it, and then forward it to the next sensor. Links are typically bidirectional, which means that when sensor A can hear sensor B, it's also true that sensor B can hear sensor A. What do I mean by broadcast? This means that when a sensor transmits, any sensor within hearing range, no matter which direction it is in, can receive its transmission. When you go smaller, when you're talking about smart dust, which is a really small, smaller than a penny sensor node, RF is not necessarily attractive because it has high frequency and it consumes a lot of power. And at those small form factors, you really don't have enough energy saved up in your battery to support RF communication. Instead, you want to support optical transmission. Some of these smaller models support optical transmission. This involves simpler hardware and it consumes lower power. However, it comes with a few challenges. Here, optical transmission essentially means that you have a laser, right? You have one sensor sending its packets via a laser to another sensor, and this means that you don't have a broadcast medium anymore. You have a directional antenna, and you need to make sure that the laser is pointed at the receiving sensor. Broadcast is very expensive. You can't necessarily send out a packet to all of the sensors in your hearing range. You need to direct it to every sensor that you want to send a packet to. Line of sight is required. Laser cannot go through walls, so you need to make sure that the receiving sensor is within viewing distance of the sending sensor. In some cases, you may need to move antennas around because if you want to direct the laser accurately at the receiving sensor, this involves mechanical antenna movements that might use up a bit of energy. So switching links might be costly. However, one of the advantages is that you can use mirrors to go around walls. So you can use an intermediate sensor which simply reflects your beam. This is known as wormhole routing, where the intermediate sensor is not storing and forwarding packets, unlike RF communication, but instead is simply routing your packet as is via a mirror. So this is fairly fast. Finally, links are unidirectional. So sensor A being able to send to sensor B doesn't mean that sensor B's laser beam, optical transmission beam, is directed at sensor A. It may be directed somewhere else. So to summarize the sensor node discussion, the size of these sensor nodes is very small. It's a few millimeters to a few inches. They have limited processing and communication. They are very puny, just a few megahertz of clock, just a few megabytes of flash, just a few kilobytes of RAM, and a few tens of kilobits per second of wireless, in some cases a few hundreds of kilobits per second. They have limited power. They're typically running on batteries, and you cannot recharge those batteries in inhospitable terrains. So you need to be sure that you conserve energy when you write code for these sensor nodes. They're also failure prone, and both these nodes are failure prone, as well as the links are failure prone. So if you deploy this in the battlefield, a tank might run over it and destroy it. If you deploy it in the forest, an animal might come and destroy it or just eat it. Also, the links are failure prone, so if you send out a packet over the wireless medium, it might get dropped because there is noise in the wireless medium. But of course, they are easy to manufacture and deploy in large numbers, and so you need to offset this with protocols, distributed protocols, and operating system design that are scalable, that scale to very large numbers of these sensor nodes talking with each other, and also that are fault tolerant, that work, where the protocols work in spite of the fact that some of these sensor nodes might fail. So what about the operating system? What operating system do sensor nodes like this run? Well, there's a few considerations here when you want to build an operating system. First, you want your operating system to be small because you only have a few kilobytes of RAM, 4 kilobytes of RAM on the Mica mode. You need your operating system to be compact and fit in memory very compactly. Embedded operating systems which run on intelligent washing machines and intelligent microwaves, for instance, are not applicable because they use several hundreds of kilobytes of read-only memory or hundreds of kilobytes of memory, and they won't fit on the sensor mode. You need to worry about what your workload characteristics are. For these sensor modes, typically the workload characteristics are bursty. Typically the sensor modes are not doing anything until something interesting happens in the neighborhood. For instance, there is a tank movement or there is some rumbling on the surface of the volcano. You want to reuse these same sensor nodes. You don't want to build a sensor mode that is specifically built for the volcano. You want to reuse the same board for the enemy battle tank deployment as well. And finally, you need to worry about scheduling and real-time characteristics where you want to process things very quickly. Of course, you want to make sure that your sensors don't consume much power and that the communication is also optimized. So all of these requirements were summarized by researchers at Berkeley who built the operating system known as the TinyOS operating system for these small devices. So the Mica mode over here is running TinyOS operating system. The Mica Dot is running a TinyOS operating system too, and many versions of the Intel mode are also running a variant of the TinyOS operating system. So the fact that you need bursty data flow driven computations, the fact that you want to support multiple data streams, the fact that you want real-time computations and power conservation, as we have discussed on the last slide, all of these led to TinyOS being an event-driven execution, a reactive mode. So unlike your workstation and laptop, which are always running some process all the time, these modes might actually go to sleep when there is nothing interesting going on in the neighborhood. When something interesting happens, these modes then react and then might undertake some computation in order to react to that stimulus. Also, you want your OS to be small, operating system to be small, and you want to accommodate a diverse set of applications. And these led the researchers to build a modular operating system with modular structure and components with clean interfaces between these components. So in order to program these TinyOS modes, yes, you can program these. You use a language called NestC, which stands for Nested C. It's a variant of C. So if you're familiar with C or C++, NestC should be fairly easy. NestC defines components, and a component can be either a module or a configuration. A module specifies a set of methods and some internal storage. This is sort of like a Java class. Essentially, it is a Java class with its own internal storage, a few fields and a few methods to access those fields, but it's a static Java class. And why do you want a static Java class? Because you have limited memory. You don't really want dynamic memory allocation on these small devices. You could write a module that corresponds to a hardware element. This would be sort of like the device driver for that element, for instance, for the clock or for the LED, or to a user-defined software module, for instance, for the routing protocol among the sensors that are connected in the network. Modules implement and use interfaces. This is just like your regular Java classes, so that other modules can then call the methods in this module. So now you can wire these modules together by having one module call the methods in another module, and this together is called a configuration. Okay, so a program that you write where you have multiple modules that are talking with each other by calling each other's methods, that would be called a configuration. A complete NESC application consists of one configuration where you have multiple modules in there talking with each other. So component invocation is event driven, which means that components don't start executing just by themselves. They start executing only when they are invoked by some other event. So for instance, when something interesting happens in the neighborhood, when there is a vibration, for instance, the acoustic sensor might come into play. That particular module that runs the acoustic sensor might run. It might then call the routing module, which might then transmit a packet over to another sensor mode. You have static allocation here only. Here you typically don't have dynamic allocation because you don't want to have runtime overhead being incurred when you have only limited amounts of memory available. You can also do real-time scheduling, both hard real-time scheduling where you have deadlines for tasks, as well as soft real-time scheduling where you have soft deadlines for tasks. And finally, you have explicit interfaces by these modules so that you can accommodate different applications. A routing module that you write for the volcanic deployment could be reused in the enemy battle tank deployment scenario as well. Once you've written your application, and this discussion applies to the Mica mote over here, you would write your application on your laptop or workstation. Let's say that's your PC. It would be an SC program. You would compile it to an executable for the mote. You would then simulate it and debug it on your PC itself, on your workstation, laptop, whatever, but before deploying it on the mote itself. It's easier to simulate it on your workstation and easier to debug it there. TinyOS typically comes bundled with a TinyOS simulator known as TOSSIM, which allows you to simulate hundreds of sensor modes talking with each other and executing your program so that you can now debug your application very easily. Then typically for the Mica mote, you plug your mote into the port on your machine. So you plug your mote in here, and this would go into your machine, and you would download the program onto the mote, and then it's running your program when you switch it on. Some of the newer versions of motes allow you to download the program wirelessly over the wireless link onto the mote itself. When you turn on your mote, it is running your application. Most of these motes run only one application at a time, but you can modify the TinyOS operating system to support multiple applications running as well. So what about energy savings? So these have very limited battery supply, and they are typically running in scenarios where it's difficult to recharge them. So these modes, like the Mica modes, come with multiple power saving modes. They could either be active, idle, or sleep. Sleep means, typically the Mica mode is asleep. It might wake up after a while, or it might wake up when one of the sensors goes on. Active means that the Mica mode is sending and receiving messages. Idle means that it is alive, it's awake, but it's not necessarily doing anything interesting. It may be computing something, but it's not sending and receiving messages. Now, there is a tremendous variance in energy supply and demand. You could use batteries, you could use solar cells, you could use vibration to power your batteries and recharge your batteries. And in some cases, if you're deploying these sensor modes, some of these sensor modes in a building or in a bridge, you might actually be able to use power off the wall, of the AC socket of the wall, to charge these. So you don't necessarily need to worry about recharging the batteries or replacing the batteries. In essence, you need to worry about sources when you think about what your deployment requirements are. If you have a long-term deployment requirement where you're deploying these in inhospitable terrains, then you want to make sure that you're conserving power. If you have a short-term deployment, then you could worry less about power. Also, how much bandwidth is being used by your application is another thing that you need to worry about. Some numbers here from the 2AA batteries being used. This consumes 200 microamps of average current. This may not mean much in this particular scenario, but it's an interesting fact. So the TinyOS itself is a fairly small operating system. The software footprint is just 3.4 kilobytes, which fits just about perfectly on the 4 kilobytes of RAM that is there on these Mica modes. But this also means that you can't really load a lot of data. You need to process data rather than just store data on there. Power saving modes, as we've discussed, are active, idle, and sleep. Among all the capabilities on this Mica mode, the radio transmission is the most expensive. It consumes the most power. It consumes 12 milliamps of power. The second highest power consuming capability is the CPU being active, where it's computing actively, which consumes only 4.6 milliamps of power. This essentially means that when you write a program for these Mica modes, you may want to prefer computation over transmission of data. So it's much better for you to compute something, compute an average, and then send over the average rather than send over the raw data itself. And this has led to many in-network aggregation approaches being used for sensor networks where these sensors are talking with each other over the wireless network. Essentially, in these network aggregation approaches, you would build trees among the sensor nodes with the base station at the root of the tree, and internal nodes would receive values from their children, would compute an average of these values or some other summary, and then transmit these values up to their parent. And finally, the base station, which is at the root of the tree, gets the summary value, the final average value. This is far more efficient than either sending the raw values over to the base station or communicating directly with the base station, which involves far more power because you're sending over much longer distances. This also allows the base station to be fairly far from the center of action. For instance, you don't want the base station to be near the volcano, you want it to be far away. So this is also the correct, sensor nodes also have the correct direction for the future technology, because today's growth rates are that the size of data is growing much faster than the cost effectiveness of storage, which in turn is growing much faster than the speed of CPU, which in turn is growing much faster than the speed of communication growth, which in turn is growing much faster than the battery. So the energy storage, the batteries themselves are growing at the smallest rate. Due to hostile environments, whether they're battlefields or the environmental scenarios, as well as the cheap fabrication, you could have higher failure rates in sensor nodes. And so you need these sensor networks to be self-organizing, you need them to be self-managing, you need them to be self-healing. When a failure occurs, you want the sensor nodes themselves to figure out new paths to send the data to the base station. And finally, you want these distributed protocols to be scalable. You want the number of messages to scale well as the number of sensors grows. So if your number of sensors doubles and your number of messages goes up by a quadratic, if it goes up by a factor of 4, that's not a good scalable protocol. You want it to be growing up linearly, if possible sublinearly, as the size of the sensor network grows. In general, related to this direction of sensor nodes are a couple of other directions that have also emerged recently. ASICs, known as application specific integrated chips, are chips that are built for specific applications, and those can be used on these sensor modes. FPGAs, or field programmable gate arrays, where you can actually program the hardware itself for a specific application, have also emerged in the last few years. These are of course much faster because you're moving a lot of capability and functionality into the hardware, and anything that you can put into hardware is much faster than doing it in software. Sensor nodes are cheap and battery limited. You can deploy them in inhospitable terrains, whether they're enemy battle tank deployments or around the periphery of a volcano or in an island to monitor heat and humidity. But you need to conserve power because it's difficult to recharge these sensor modes frequently. So you need to be smart about the design of the operating system, and the TinyOS operating system has been built exactly for this. And you also need to build distributed protocols very, very well. We've discussed the design of TinyOS and a few challenges when it comes to designing distributed protocols for these scenarios. Related to this discussion are a few other topics that you can look up. The Raspberry Pi and the Arduino platforms have emerged in the last few years, which allow you to program small manageable computers very easily. And you might want to look these up. These are very interesting topics if you have not heard about them. Home automation systems use a lot of sensors. These include companies such as Nest, Amex, HomeLogic, Honeywell, etc. Typically, these are sensors that control the temperature in your home or control the locks in your home. The power concerns are smaller because they're typically connected to AC power, but you have security and accuracy concerns here. You want your home automation systems to be accurate, to let you in the door, to set the correct temperature when you so desire. Typically, it's possible to network these devices together in your home. These are known as Internet of Things. That's a key phrase that you might hear. Essentially, this means that you're networking many devices or many of these sensors together into a network, and you're then managing them over the network. Often these are known as cyber physical systems. When you have human beings involved along with sensors and devices networked with each other, these are known as cyber physical systems. Cars and vehicles today, for instance, have become networks of sensors, where you have sensors at the tires monitoring the pressure, you have sensors in the engine monitoring the status of the engine, and all of these are talking with each other and are then relaying the alerts to you on your dashboard when you're driving. These combinations of humans and machines are often called cyber-physical systems, and these are becoming more and more widespread. For instance, in operation theaters and hospitals, doctors are increasingly using machines around them to make sure that there is more accuracy and in the operations itself, and that the doctors being assessed are being assisted as much as possible.